Yeah, thanks, Phil. So good afternoon, everyone, and welcome to the process engineering session for the Bernal Institute Research Day 2020.
Sorry, just give me a second. I'm sorry.
Sorry.
Yep. And now, yeah, you're online.
Good to go. Yeah. Good afternoon, everyone, and welcome to the process engineering session for the Bernal Institute Research Day 2021. I'm delighted we have two distinguished female chemical engineers to present to us this afternoon. We have Professor Claire Adjiman from Imperial College London and Professor Marianthi Ierapetritou from University of Delaware. Both Claire and Marianthi have been with us before as international SFI reviewers for SSPC, but they are both most welcome back to Limerick in this less formal capacity here today. So for everyone, there's an announcement function on the left-hand side of your screen. If we have time for questions at the end of each presentation, we will take some. If we don't have time for all questions, we will be timed out of this session at 4:05 GMT. However, all comments and questions will be logged and distributed to the team here. Our first presenter is Professor Claire Adjiman from the Department of Chemical Engineering, Imperial College London. And the title of Claire's presentation is Molecular Engineering for Process Development. Claire, you're most very welcome back to Limerick, albeit virtually, and the floor is yours.
Thanks very much, Gavin. Hopefully I'm live.
You're not yet.
Okay.
Just give me a second.
Mm-hmm. Tell me when.
Yep.
Okay, good afternoon or good morning, everyone. Thanks very much, Gavin, for the introduction. It's really a pleasure to be back, so to speak, although I'm really sorry not to be able to enjoy the Irish hospitality I've benefited from a couple of times on this interview. So thanks so much for the invitation. I just want to present an overview of some of the work we've been doing on integrating molecular and process design. And I want to start off by motivating the work a little bit and trying to see why it's important to integrate those two scales of operation. And then I'm going to talk about the work we've done through examples. I won't have much time to go into the details of how we do things, but hopefully I can give you a flavor for that. And we look at some quite different examples. One, we look at the selection of fluids for organic Rankine cycles. And then we look at solvents in terms of reaction solvents and then crystallization solvents. So it will not come as a surprise to many of you that solvents matter when designing processes. And some work by Rasmussen and co-workers has shown that solubility, for example, is very much dependent on the choice of solvent, and that for solvent mixtures you can see a maximum in solubility. This is for paracetamol in mixtures of acetone and water, and you can do much better than acetone by adding a bit of water, even though paracetamol is barely soluble in water. So that's very encouraging for process development, but we also have to think about how much solvent is left in the final product. We have to think about the impact of the solvent on crystal shape. We have to think about the safety of the process and the impact of the solvent on that, the ease of processing, so for example, viscosity, and we have to also think about yield and the use of raw materials and solvents as well. So for example, for this ether synthesis reaction shown here, the selectivity to the ether varies widely between acetone, where it's 95%, and 1,4-dioxane, when it's only 24%. So solvent choice, as you can see, has quite a complex impact on a process. The other thing to think about is, so how are we going to decide what solvent to use for a given process? And the first approach to this might be to use property metrics as a way to identify promising solvents. So this could be other processing materials like catalysts or membranes and so on. This is easiest to do because we have a sense for what properties impact the process. So I've mentioned solubility, I've mentioned viscosity, for example. And so we could say, well, we want a high solubility, we want a low viscosity, and try to find the best solvent in that way. And indeed, we've tried to do that in some contexts. So, for example, in the context of chemisorption of carbon dioxide from natural gas or from flue gases from power stations. And if you compare the performance of different solvents, as shown on the left here, so they're just the names of those solvents. I'm just going the wrong way here. So if you look at the performance in terms of different properties like the molar volume or the surface tension or the heat capacity compared to monoethanolamine, which is a standard solvent for this process, you will see in red solvents that do worse for that property, and in blue when they do better for that property. And so you can take two properties that have an impact, for example, on the size of the absorber, the molar volume and the surface tension. And these seem to go in opposite directions. So it's difficult to say whether this solvent here, for example, would be better than MEA in terms of absorber size or worse than MEA because we don't have that quantitative information. So there's a limit to what we can do with properties. The other aspect to bear in mind is that by making the properties better, we don't necessarily get a better process. And here is some work that we've done in the context of water desalination, so trying to develop a reverse osmosis process made up of multiple membranes in parallel and in series. And if you look at the cost of the water per barrel, which is shown here on this axis, versus permeance, you can see that as you improve the permeance of the membrane, you initially get a decrease, especially in the capital cost, shown in blue here. But at some point, you get diminishing returns for your efforts to get an ultra-permeable membrane. And so you then need to look at other reasons why the process is not doing better. And you'll find that this is due to concentration polarization. And the way to deal with that is to focus on the fluid flow near the membrane. So it's not looking at the membrane properties anymore. And so we need to understand that interaction between the properties of the materials we're using in the process and the performance of the process. So what we need to be able to do is to recognize that choice and develop integrated approaches to molecular and process design. So if you have as your design space, the space of molecules or materials that you could be using for your process, but you also combine that in your design space with the process unit you could be using and the operating conditions like the temperatures, pressures, compositions, flow rates, the sizes of the equipment, and so on. This is the design of possibilities. So whereas traditional process engineering will focus on equipment and conditions, we're trying to expand that to embed also the molecular choices that we're making in process design. And so the blueprint for the work that we do is to combine this design space and to pose a design problem, which would be a mathematical problem of some sort, an optimization problem, trying to maximize some performance metric. Feeding into that problem, we have predictive structure property models that enable us to go from molecular structure to physical properties. And these are very key and not often easy to find. And we will have process models, which are your standard chemical engineering, mass balance and energy balance equations. Together with your design objectives and constraints, that forms your design problem. We will solve this problem to generate a random list of possible options, possible molecules. And for each molecule, we will have the optimal conditions of operation, the optimal temperature, so that may vary. And so we let the molecule do its best. We really give it free rein and optimize the process around each possible molecule here. And then typically the models we're using for process models are a bit rough here. So we then need to do some experimental verification. If that agrees with what we've found so far, we can proceed. If it doesn't agree, we need to go back to our design problem. So if it agrees and we found a good molecule, set of molecules, we'll then proceed to detailed design, and maybe we'll do some, for example, thermodynamic measurements on the particular solvent we've chosen. So this area of work is what we call computer-aided molecular and process design, the idea of formulating these problems and solving them, developing the appropriate structure property models. For short, we call this CAMPD, and this is what I'm going to be talking about in the next few minutes. Some of the challenges we encounter in trying to develop these tools that embed not only the standard process synthesis and process design decisions, but also the molecular decisions are as follows. First of all, it's quite challenging to get some meaningful design metrics. We need to think about the process economics, we need to think about the sustainability of the process, and we need to link that back to the molecular structure, and that can be very difficult to measure. We face some rather complex solution strategies because as we're changing, for example, in an absorption column or in a crystallizer, we're changing the solvent and we're letting the algorithm change the temperatures and the solvents. We have no guarantee that the solvent will be liquid as we'd expect in the process unit at that point. And so that may lead to failure of solving the problem. And so we need to control that somehow. We want to rest upon the significant advances that have been made in property prediction in recent years. So we want to use things like computational chemistry, molecular simulations, and so on if possible, but those are very expensive, and so that's challenging to integrate in a process flow sheet. And finally, we want to take into account the uncertainty that's inherent in our models and to that has on the solutions we are finding. So I'm not going to go in detail as to how we address these different challenges. As I said, I'm just going to give you a flavor of how far we've got through some examples. And the first example is around the design of organic ranking cycles. And here we want to explore a vast space of fluids. So we really want to go to town in terms of the number of compounds we're looking at. And we're going to do this through a group contribution equation of state that we've developed in our group. Called the Safka-Mami equation of state. So here we're playing Lego with atom groups and we're combining them to make different molecules and predicting their phase behavior and their thermal properties without ever having to synthesize those molecules. The advantage of this equation is that it's very cheap to evaluate. It's an equation of state, so it doesn't require as much computational effort as a molecular simulation. Nevertheless, because of these issues I've mentioned of changing the temperature and the phase of the fluid, we need to have some really sophisticated algorithms. So just to give you an overview of organic Rankine cycles, in their most basic form, we take a waste heat source, so a rather low heat, low grade source. And so we start at this point 1 here, which can be on the temperature entropy diagram can be seen here. And so we'll be in the liquid state, and we're going to compress this fluid. We're going to put some work into the system to compress the fluid and take it to an evaporator. We're going to vaporize it. And then when we've done this, we're going to pass it through a turbine and we're going to recover some work out of this. So the idea is that we have more work here than we've put in to the system. And then we're going to go back and recondense the fluid and go back and forth like this. So we're looking for a fluid that is going to enable us to do this at whatever temperature we have our waste heat available. Okay, so we need to have a fluid that has the right phase envelope to do this and the right thermal properties. It is very well known that the optimal working fluid is highly dependent on the process condition and constraints. It also depends, of course, on the configuration of the process. And we're going to focus on this most simple configuration here. Okay, so to look at some examples of how we've been able to solve these problems and what are the challenges here. We started in all cases with a very large design space that contains a number of groups that we can combine to make nearly 59,000 different molecules. And so looking at different case studies that have different temperature ranges for the sources that we've got. So for example, a fairly narrow range here of 20 to 110 degrees or a wider range of 20 to 200 degrees, you can see that that has a big impact on the number of molecules that are feasible as fluids. Only 48 in this narrow case and 263 in this case here. So you can imagine that we would have many failures if we didn't take into account the fact that we may have fluids that are unsuitable in this large design space. We're trying to maximize the net power output for our ranking cycle. And so for the two cases, the feasible molecules are ranked here in terms of their output. And you can see that we have a very sharp decline in the number of fluids here. And so it really is important which molecule we're using as an organic ranking cycle fluid. Looking at another case where we have a solar collector. So in this case, we have a hot source with a constant heat input, but an upper temperature on the working fluid, which is bounded by an upper bound here of 80 degrees Celsius. So here we have an extremely narrow range of temperatures. And with the same number of candidates, only 26 are feasible in this case, and we're able to identify them. And you can see in this case, we're optimizing the thermal efficiency, and we are trying to we're finding a few more fluids that have high efficiency in this case. Okay. Now, what this case illustrates quite nicely is the danger of just looking at properties as a guide to selecting a working fluid. So, for example, we might say that we're looking at working fluids that would have a low heat capacity. And what this diagram shows here is the average value of each property. So you have, for example, density, heat of vaporization, and so on, over the 26 feasible compounds. In blue are all compounds, and in red are the top 10 compounds. And the solid red dot is the best compound that we've got here. And so if you look at this, you can see that actually many of the compounds, so for the liquid density, for example, for the critical pressure, actually the compounds that are optimal, the top 10, are pretty much average. They're not really particularly extreme, and especially the best one has very average properties. So trying to maximize or minimize its properties wouldn't really tell us which compound works best. And so by integrating the property prediction with a process model, we're able to quickly, in a matter of minutes, screen these thousands and thousands of molecules and identify the top few. And so that's very nice, and we'd like to be able to apply this to different settings. And one context we've done this, where we've had to work a bit harder for property prediction, is for the computer-aided design of reaction solvents, trying to optimize the rate of reaction, maximize their rate, trying to maximize the selectivity of reactions. And we've done two things here to look at the impact of solvent on kinetics. We've used either quantum mechanical calculations or experiments in our design loop. And so the methodology that we use here is very similar to what I've described, but we need to embed our property prediction development in the loop. So we have our initial space of possible solvents, and we select a few of these, perhaps 6 to 10 solvents, and we either do some quantum mechanical calculations or some experiments in those few solvents, and we obtain the rate constant for those solvents. We then use that to build a surrogate model that is a simplified model, much faster to evaluate than experiments or quantum mechanics, but that gives us the ability to predict what will happen in other solvents. And this is what we embed in our design problem. So we take this surrogate model, we build a design problem as before, we solve this problem and get a list of candidates. If we found new solvents in this list, we are going to verify that our model was good. And so we're going to either measure or compute by quantum mechanics the rate constants and go back around this loop. Once we don't find a new solvent, we're going to then verify the best candidate solvents experimentally. So let me quickly show you a couple of examples of this. The first is a very classic reaction to study solvent effects. I mentioned SN2 reactions. Of course, SN2 reactions are very relevant industrially. And so we're looking at the specific reaction shown here, specific scheme, phenazole bromide and pyridine reacting to form phenacyl pyridinium bromide here. Okay, so a quaternary iron salt. And we're asking in which reaction, in which solvent is the reaction fastest. We chose this reaction initially because we sort of know the answer, because it's been very well studied, at least as a reaction class. And we know that the greater the dielectric constant, the faster the reaction. So we can test our algorithm that way. We consider a design space of 40 functional groups, and we avoid potentially reactive groups. So for example, we have no amines. We include some constraints on the boiling point to make sure the solvent is liquid. And we can also add things like reactor design, environmental performance indicators, toxicity indicators, and so on within our optimization framework. This example, we did some quantum mechanical calculations. So we take an initial set of 6 solvents shown here with different dielectric constants increasing from top to bottom. And we see that indeed the rate constant increases from low dielectric to high dielectric. And we then get cranking on this design framework. We build a surrogate model, find the first candidates, update the model. And we do this for a few iterations. So we go around this loop about 4 times here. So our initial compound is iodonitromethane, and we actually see something which is kind of middle of the road in terms of performance. And we bounce around a little bit until we converge to nitromethane. And you can see that's a 40% improvement on acetonitrile. That's significant because actually those 2 compounds have exactly the same dielectric constant. So we wouldn't know just by intuition which one would work better, and we wouldn't necessarily expect that we can get 40% improvement in reaction rate constant. So we've done only 10 quantum mechanical calculations by the end, even though we explored a space of over 1,000 potential solvents. And we have been able to verify this acceleration experimentally, and we to get about 40% acceleration. Another example of what we've done in this area is with the experiments in the loop. So here we were looking at selectivity in this SNAR reaction here. And selectivity is known to vary quite a lot with solvent for this particular reaction, but also, and so you can see that here for the 9 solvents where we've done experiments. You can see there is no obvious trend with dielectric constant in this case. And the rate constant for the desired product does increase more or less monotonically, not quite, but more or less monotonically with the dielectric in this case. Okay, so we've done these in situ experiments by NMR for the 9 solvents, and we then go around the loop building a surrogate model and identifying optimal solvents. And so the problem that we pose is to maximize both the rate of K0 as well as K-ortho, sorry, as well as the selectivity of the ortho with respect to the para product. We have bounds on the boiling point and melting point of the solvent. We look at toxicity, octanol water partition coefficient, and flash points to look at the health and safety of the solvent. And these are the results that we are able to generate. So this is the rate constant here and the selectivity at the bottom. Ideally, we want high rate, high selectivity, so we'd like to be where that star is, but unfortunately, reality doesn't allow us to get there. What we can do very quickly computationally is generate the performance of many, many different solvents. So the dots that you see are calculations we've done, and these are very quick calculations. But what we're most interested in our optimization are the open circles. These are solvents from which, if we want to improve one objective, we must lose in the other objective. So for example, starting here, to increase the selectivity, you can see that we have a drop in the rate constant, and vice versa. To improve the rate constant, we have to sacrifice the selectivity. Okay, so these are so-called Pareto optimal points, all these open circles, and they correspond to trade-offs between selectivity and rate constant. And so this enables us to then make choices as designers for where we want that trade-off to lie. And we have verified one point in this on this domain, which is this one here, and we found good agreement with the predicted performance. So that gives you an idea of how we've applied these 2 reaction solvents and how we've integrated experiments of quantum mechanics in our design loop. What I want to do as a last example is to look at crystallization solvents, which I know is of interest to many people at the Bernal Center. And so we are interested here in the interactions between the solvent and process variables. Once again, we're going to choose solvents from the list rather than building them like Lego in this case. And we do design solvent mixtures, but I won't be showing you an example of that in this particular case. What I want to explore, though, is the role of solvent and the impact of solvent on shape. And I'm going to do this through the crystallization of alpha-glycine. So I'm interested in maximizing the crystal yield, in minimizing the aspect ratio, so it should be greater than 1, but as close to 1 as possible, and also to look at solvent use as a potential metric, and to look at really compromised solutions between yield and aspect ratio. I'm going to consider solvents in the chemical classes shown here, and because I'm working from a list of solvents, I have specifically a list of 21 solvents that belong to these classes. So I want to have as little experimental input going into my problem as possible. And so what I'm going to rely on, though, I can't get away from that, is the melting point of the API and the heat of melting. I need its crystal structure to be able to predict the impact of a solvent on its shape. And I need also the experimental melting points of the solvents, because we don't have very good methods to predict those. But I don't need their boiling points or any other solvent properties. I'm going to predict all of those. I don't need any solubility data either. What I want to get out of my model and my problem is the optimal operation temperature. So I'm going to look at cooling crystallization in this case. So I want a starting temperature and an end temperature. I want the optimal crystal yield. I want to know about solvent consumption. And of course, I want to know which solvent is going to work best for me. And I want to know what is the crystal aspect ratio. So I'm going to use two different sets of models here. I'm going to have thermodynamic models based again on the Saft equation of states, which equation of state that I mentioned at the beginning. And I'm going to be able to predict things like solubility and boiling point from this equation. And then I'm going to use the method developed in the group of Mike Doherty in order to predict what crystal aspect ratio I might get. So there's a whole lot of calculations that I do a priori on the API, but once I've done those calculations, we've developed a set of equations that allow us to say how the crystal is growing depending on the solvent that we have. We put all of these equations within GPROM, so you have a single environment from which to solve the optimization problem. And so let me just show you some brief results on this. So I'm showing you my two objectives here, the crystal yield here, which I want to be as high as possible, and the aspect ratio, which I want to be as low as possible. So if I look at maximizing the yield, I find heptane is best. However, it doesn't have a very good aspect ratio. And I think I find water is best in terms of aspect ratio, but I don't get a great yield. So I clearly have some trade-offs here. Ideally, I want to be in this top corner here. Unfortunately, I cannot get there, but I can use my other solvents to try and get as close as possible. And so this is an evaluation of the different solvents here, but I don't have to evaluate all of them. I can just focus on the best ones through optimization. And the points that are as diamonds here are the points that are Pareto optimal, so where you have a real trade-off between the two objective functions, and their names are listed along the way as well. And so you can see how close we can get to this corner here through these different solvents, and you can see that we have quite a lot of variety of solvents here. The important thing here is that the performance of each solvent is determined by not only changing the solvent, but changing the temperature of operation and also changing the supersaturation of the solution in the crystallizer. And so while we have a fairly simple model of our crystallizer, we're not taking kinetics of the crystallizer into account. This gives us an initial assessment of which solvents we should pursue further for design. If I take into account solvent use and I try to limit that, I end up finding that ethanolamine, ethylene glycol, and water are the most promising solvents. So I can add additional layers on this picture as well. So I've shown you quite a few examples of integrated molecular and process design, and hopefully I've convinced you that that can lead to improved process performance, and that it is quite important to take into account the interaction, the interplay between process variables and molecular variables, molecular structure. This is only possible if we have the right predictive structure property models and ways to embed those, even if they're quite expensive, like quantum mechanical calculations. And if we have tailored algorithms to overcome infeasibility, because most of the molecules we're interested in are actually not going to be, or that we want to evaluate, are not going to achieve the performance we want. So we've been working for a number of years on automating these integrated design problems and solving them, and showing this for a range of examples. So I've shown you today heat recovery, crystallization, and reactions. We've also done work on absorption and liquid-liquid extraction. And on crystallization, we've also looked at the integration with washing and isolation, so looking at the whole chain together. And currently we're working to extend that to reactions as well, to minimize the amount of solvent use and solvent swaps. The framework that we have developed can also be applied to product design, and we've worked a bit on adhesives and drug delivery systems, in particular polymersons for drug delivery in this area. And I just want to end by thanking the very many people who have contributed to this, PhD students, postdocs, and collaborators, as well as our funders for this work. And if there is time, I'd be delighted to answer some questions.
That's great, Claire. A virtual round of applause. Fantastic presentation. We in the group chat here, we've got a question from Sarah Gurin, and Sarah's asking, is there any particular QM model or software that works best for this? And did you have to do much model benchmarking? Oh,
that's a great question. So in the work that we've done, we're quite big fans of the SMD model developed by Marianthi, Kramer, and Truller. So we've used that within the Gaussian software, but you can use it in other software. Yes, we are very keen on benchmarking. It's something that we believe is really important. So I can't say that it works systematically in terms of giving us the accuracy that we need, even the qualitative ranking that we need. So we do some benchmarking. I think you can get away with benchmarking a couple of solvents rather than having to benchmark many of them, is what we're finding recently. And of course, the Cosmo method has been growing in popularity. So you'll find in the literature a growing number of publications on the design of reaction solvents that use Cosmo. But there isn't always benchmarking. So I think that's the question to bear in mind in reading all the literature, is to what extent the results have been verified. For thermodynamics, I think we're quite confident, but for kinetics, that's still very much work in progress.
Great, that's fantastic. Claire, again, thanks a lot for presenting. It's short notice for our Bernal Research Day 2021, and no doubt I'll be seeing you in the future on SSPC type activities at some stage next year. So thanks again. Thanks a lot.
Thank you. Thank you very much.
So our next presenter is Professor Marianthi Ierapetritou from the Department of Chemical and Biomolecular Engineering at the University of Delaware in the US. And Marianthi's presentation is towards a digital twin, advances in process modeling and integration of pharmaceutical manufacturing. Marianthi, you're very welcome back in Limerick, and the floor is yours.
Okay, thank you so much, Gavin. Can you hear me well? Am I live?
Yep, perfect. Yeah.
Okay, perfect. Let me go into the. Okay, so and you can see my slides fine?
Yep, perfect.
Great, thank you so much. I do also share the opinion of Claire that it's nice to be back, but the truth is I would very much prefer to be there in person. I hope that I will have this chance sometime in the future, hopefully in the near future, that everything, all of those things have been resolved, I hope. So it's great that actually Claire talked before me, because I'm going to take you to the manufacturing, to integration of different units. So before the other talks of the other sessions today were more focusing on the molecular, I'm more focusing on the process design, integration of different units and manufacturing. So I think, Claire sit very well between those two scales, right, to bridge the gap between these. So today I'm going to discuss with you some ideas regarding what we've seen very, very popular in the literature, which is the concept of digital twin. I would like to start always my presentation by acknowledging the group of my students, because those are the people that are doing the work that I'm presenting today. So in particular, as you saw also from my title slide, Yinzi, O, and Puja were the people that actually his work is highlighted in this set of slides. Also, you know, our work basically, before I go into very much deep dive into more in the manufacturing and digital twin applications, we have focus in my group in process modeling, optimization, incorporation of uncertainty in different applications, including biomass conversion to chemicals, integrated decision making, going more towards the level of supply chain management. And I'm going to talk to you today about the pharmaceutical manufacturing. So before I start, just briefly an outline of my presentation. I would like to just cover the concept of digital twin. Most of you have seen a lot of publications that appear in the literature, number of presentations for academics and industrial colleagues. So I would like to give you a little bit the idea about that, and then focusing on what are the different components that we need in order to develop a digital twin. So one question that I had when we first starting looking at these concepts is basically, so how is it a new concept? And actually it turns out that it's not a new concept. We have seen this appearing in the literature even 30 years ago, and in manufacturing we have Michael Greaves turned the coin of digital twin back in 2002, so almost 20 years ago. So and you see, if you look at the literature, you see a number of different definitions of what is a digital twin. One that I think represents well what I believe that it's a digital twin is what I saw here, which is that basically it's a visual information construct that fully describes, and that's very important, the potential and the actual physical manufacturing product. And also would like to point out here a potential, because it's also, you know, you can have a digital twin of a product that has not been manufactured yet. So what is basically the big differentiation factor between a digital twin and the simulation is the fact that you have this two-way communication between the physical object and the digital replica. So, of course, I mean, you know, since these concepts have been already appear in the literature, one question that appears is basically, why now? Why do we have this spark of interest in the literature about the digital twin? And I think what the main reason is basically the fact that we have a development of the technology that enables the development of the digital twin. If we like to decompose the different concepts that appear in the digital twin, is basically the fact that you have to have the capability of getting the data, so have all the PAT, all the analytical technology to get the data. You have to have the computational power to store and also be able to access it and be able to then analyze the data using algorithms. So all of those components are actually very required in order to get to the target, which is the digital twin. All of those components actually are components of what also appear very often in the literature, what they call the fourth industrial revolution or Industry 4.0, which is basically the utilization of cyber physical systems in order to be able to utilize the information that we get. And here I have just a historic slide to just present briefly what were the different industrial revolutions over the years. So in terms of pharmaceutical manufacturing, we have the digital twin. The concept of the digital twin is basically the representation of having the physical plan with all the information that we can extract. The physical plan is not only the equipment, it's basically the operations and also the PAT technologies, which is basically the sensors that you have, the communication with the control platforms. All of those components are actually what consists of the physical plan. On the other hand, we have the virtual plan, which is I'm going to talk more about in the next few slides, which can perform a number of activities, but the main idea is that it has to be an exact replication of what you see in the physical plan. And there must be a communication, two-way communication, as I already pointed out, between the physical plan and the visual plan. So just to give you an idea, as I said, the first component of a digital twin is basically the data. So you need to be able to get the data, which represents, as I illustrated here, which is how we get the data from a pilot plan that produces tablets from a granular material. So you have the process equipment, and this then is connected to a control software. Here we have, for example, Delta V, can be other systems, and this has been communicated to the data historian. So as you store this data and you can analyze it and you can communicate it then with the visual counterpart. You have the PAT sensors, and this has to be communicated usually with an OPC server that also talks to the historian. Everything has to be then stored in a cloud server and communicated with the model. On top of this, what you see in the right-hand side is also the fact that we'd like to enable the storage and the capture of the information from the laboratory. So things that Claire was talking about the material property database, analytical experimental data, those can play an important role on fitting the parameters, and I'm going to show you a little bit about this in the models. And actually, Claire talked a lot about this, and all of these components should be stored and integrated in the data in the data platform and the database, so as it can communicate it with the process model. The next component is, of course, the models. But before we go into the models, I would like to just place the models that I'm going to illustrate in the overall pipeline of the drug production. So from the manufacturing of the API and the excipients, the work that Claire described actually fits into this category. The downstream product development, where basically you formulate now the product, and then the drug performance, which involves more pharmacological modeling. So as you move to the right, you have more on the product performance, and when you move on the left is basically product design. So what I'm going to focus today is basically the middle, which is the product development. So all the different tools and the digital twin that I'm going to present, at least the enabling technologies, are basically described in this box. So going into the modeling, so as I pointed out, this is the next enabling technology. There are multiple levels of models that you can have. One is basically just take the process inputs, the process outputs, and try to find relationships that connect to this. Then the second level is basically incorporating material properties and see how this can change during the process, or basically how can change your output of the process. And then if you combine material models and the process models, you get to the level 3, which are the models that we are developing in our group over the years. So we have been working in this area for a number of years, and we have been developing models to describe different modes of producing. And here I'm focusing on granular materials and the production of tablets. This is a direct compaction line involving like feeders, the commill, the blenders, and the tablet press. So for each one of these unit operations, we have developed semi-mechanistic models. The reason why I said semi-mechanistics are basically, we have some equations, for example, for the feeder, the feed factor model that how takes into consideration how the unit operates. But then in this model, there are some parameters like the feed factor maximum and minimum and the vita value here, which have to be connected with the material properties. And this happens in semi-empirical using data from our laboratories. We would love to have developed the properties or use the mechanistic modeling to go all the way to how the actual molecules interact, but this is very, very difficult for granular materials. Similar for blender and the tablet press. I'm not going to go into the details of this. We have published this work, so I will be happy to share papers with you. And then for the wet granulation, which is another way of producing tablets for materials that are not flowing very well. Again, we have similar developed semi-mechanistic models for the granulator, for the dryer, for the mill, in order to capture the input-output relations for this a little bit more complicated process. So moving on, because okay, so when you have the equations that describe the input-output relation for each individual unit operation. Now the next step in order to go to the digital twin is basically bring all those units together and develop the flow sheet model that goes from the set of input materials to the final products and captures all the different changes that you see within each unit operation. So and we have done that. We have utilized in our work most of the times GPROM's software. And so what you see on the right is basically how the different properties of the material flows through the different unit equipments. So the idea of having a simulation, because as up to now I'm talking about simulation software, is basically to enable doing a number of different things. One of these is basically criticality analysis, trying to identify what are the critical process parameters, where we should place more attention, and where the failure can come into overall line. So by having the flow sheet model, you can perform sensitivity analysis, having a set of input parameters to a set of outputs, and then use these sensitivity metrics to understand the input-output relationship. And as you see from this color map, what you identify is basically what are the inputs that are most important from the outputs that you would like to monitor through the process. Not only the final product output, but also the intermediates. Moving on, what we would like also to be able to do is analyze and understand the design space, not only for each unit operation, but actually for the overall process. So we have, and because we have this simulation to give us the where we are feasible and where we are not, we have developed this methodology that uses the surrogate modeling as a way to place additional points and be able to sample more intelligently in order to identify the boundaries of the design space. And we have done that for the continuous manufacturing line. And what I show here is basically all the different, in the multidimensional space, I have mapped this to a two-dimensional just for the visualization, but this is basically the red boundaries that you see in these pictures are basically the boundary of the design space. So within this space, you can operate efficiently and meeting the product regulatory requirements. You can also perform optimization. So we have built algorithms to enable the communication with the flow sheet model, and again, utilizing ideas of not having to sample the space multiple times, but reducing the dimensionality of the inputs functional calls, so as we can perform more efficiently the process optimization. Again, I would be happy to share the papers that we have published in this area. And for the direct compression line, for example, we have minimizing cost as one of the objectives, but definitely you can incorporate other objectives like the fact that you have to reduce the waste of the waste product, but of course you have to keep the product quality constraints as hard constraints into your problem. And this gives rise to the optimum solution that basically tries to produce as many tablets as possible with minimizing the cost. So I'm not going to go too much into the details because I don't have too much time, because I would like to move to the second, to another very important part of developing a digital twin. And this is the communication between the model and the data. So far, what I have shown is basically just one-way communication, where basically you get the data and you get the data and you fit parameters into the model. What we would like to do is to be able to get the data and update our models. So how are we doing that is just by, instead of having either a black box model or models where basically there are some parameters that we fit based on the data, we have hybrid models. So there is a component which it's shown here as a white box model that includes our mechanistic understanding, our prior knowledge of our each unit operation, and then there is a black box model which basically absorbs the additional information which comes from the operation of the plant. So, and you can construct this by multiple ways. You can have this, the black box in series, you can have it in parallel, or you can have a combination of those things. So we have started working on this, and we have focusing on different unit operations for the time being. So here I saw the result where we have used two different models like artificial neural networks to support vector machines as our black box or surrogate model for the additional data that comes from the plant. I don't know why it goes back to this. So I might have to skip my last few slides that I actually go through the similar work that we're doing in the area of biologics manufacturing. But I guess, I mean, I gave you the idea of what we're doing and some of the Okay, so I was talking about this. I was talking about the fact that the hybrid models can help you understand better the experiments, the data that are coming from the plant. And we have done that also from the blender, as it shows here. What we have, the white box, the black line is basically the model that is based only on our mechanistic understanding of the unit, but then when we are integrating information from operating the blender, then we can go closer to things that we might ignore when we were building the model. So we have starting doing this in an automated way, communicated with the plan and building the models to enable this adaptability of the model as your plan evolves over time. So what the green boxes that you see on the bottom is basically the things that we have developed the capability to do, but still we have to work on the red boxes, which is how now you communicate this additional information to the process operation, to the plants, and how this can be then transformed to efficient, not only control methodologies, but actually how you can operate the overall plan with an optimal way. So I'm going to skip the bio because we lost some time, but we have done some additional work towards these ideas in the biologics production, starting with upstream, focusing on bioreactor, building surrogate models to be able to capture the most important information for bioreactor, and then moving to connecting the different tools to bring the different units to build the flow sheet model. And in this way, we'll be able to analyze the economic benefits for going for batch to continuous processes, and then performing different scenarios by increasing the capacity of the plant, by increasing the upstream titer of the plant, and so on. So, and again, the vision for the biologics manufacturing is similar as we have for the small molecules, that we have the physical plan on the bottom, we have the process simulation with the additional capability of providing information about the design space, the sensitivity, the plant optimization, and those things communicate in a two-way manner. So with that, I would like to finish my presentation. Sorry for this unfortunate event, but this is what we're doing with the virtual reality that we're living in. I try to illustrate that there are a number of steps that we would like to take in order to go to the digital twin framework, involving getting the data, getting the models, but also establish an efficient collaboration between the two. So with that, I would like to acknowledge my funding sources. Without that, we could not do the work that we're doing. And thank you for your attention. And I don't know if we have time for a quick question. Thank you.
Great, thank you, Marianthi. A virtual round of applause from everyone. Just one quick question myself. Applying these digital twin techniques to biologics, the complexity over a small molecule or drug product type activity, it must be a daunting task, and what additional approaches do you need to take for the biologics processing piece?
Yeah, and so that's an excellent question. I mean, I know that you have been working on this area, and yes, it's a much more complicated process, and we haven't established also even the PAT technology to extract the information that we need to build the right models. So we are a little bit behind, but I think we are building the right tools now, the right sensing PAT tools, and then we can use what we know about the system to build the model. but then going also to the surrogate models and hybrid models to enable the utilization of the modeling in the biologics production.
Yeah, very good. So, Marianthi, thanks a lot again for your presentation. I'd like to thank Claire as well, and hopefully we'll see you live at some stage soon here in Limerick. So again, thanks an awful lot for your time and your attention to the Bernal Research Day. So on that point, I'd just like to close session 4 in process engineering, and I think we can all return to the conference hall where Luke has a few closing remarks. So again, folks, thanks a lot, and we'll see you soon. Bye-bye.
Thank you, Kevin.